Symmetry. Introduction. In the chapter of lines and angles and constructions, you have learned how many types of lines are there. You have been explored angles, intersecting lines, parallel lines, congruent lines, and collinear points between them. In this chapter, we will learn about symmetry and their fundamental concepts. We will also learn reflection and linear symmetry, and in the end, we will learn rotational symmetry as well. Symmetry. Symmetry means a proportionate and balanced similarity found in two halves of an object. Look at a human face shown below. What do you observe? The two parts on opposite sides of a dotted line are perfectly same. Now look at the picture of a building shown below. Here too, the two parts on the both sides of a dotted line are exactly identical. You will observe a similar trait in each of the following articles. Such objects are said to possess symmetry and are called symmetrical objects. Reflection symmetry or linear symmetry. Look at the following figure. Clearly, if the figure given in a previous page is folded along the dotted line, the midpoint of the two sides of the dotted line exactly coincide with or overlap each other. So, vertex A coincides with vertex A, vertex B coincides with vertex B, vertex C coincides with vertex C, and vertex D coincides with vertex D. Such a figure is said to possess linear symmetry or reflection symmetry. Do you think it would be correct to say that the two halves of a figure on both sides are the dotted line of mirror images of each other? Of course, yes. Now observe the following figures. Is any of the above figures symmetrical? On careful observation, you will find that none of the above four figures is symmetrical. Line of symmetry. A line that divides a figure into two parts that exactly overlap or coincide with when folded along that line is called a line of symmetry of the figure. In each of the following figures, the dotted line is the line of symmetry. Can a figure have more than one line of symmetry? Of course, yes. Here are a few examples. Clearly, figure 1 has 4 lines of symmetry, while each one of the figures 2 and 3 has 2 lines of symmetry. Examples of linear symmetry. 1. A line segment is symmetrical about its perpendicular bisector. Method. Let AB be the given line segment and let POQ be the perpendicular bisector of AB. Then O equals to OB and angle AOP equals angle VOP equals 90 degree. So AB is symmetrical about its perpendicular bisector of PQ. 2. A given angle having equal arms is symmetrical about the bisector of an angle. Method. Let AOB be the given angle with equal arms O and OB and let OC be the bisector of AOB. Then clearly angle AOC and angle BOD are identical. Hence angle AOB is symmetrical about the bisector OC. 3. A isosceles triangle is symmetrical about the bisector of an angle included between the equal side. Method. Let angle ABC be the isosceles triangle in which AB equals AC and let AD be the bisector of BAC. If ABC be folded along AD, then ADC coincides exactly with ADB. Thus, triangle ADC is identical with triangle ADB. Hence, AD is a line of symmetry of ABC. 4. The kite has one line of symmetry, namely the diagonal sole dotted in the adjoining figure. Method. Let ABCD is a kite in which AB equals AD and BC equals DC. If we folded the kite along the line AC, we find that the two parts coincide with each other. Hence, the kind ABCD is symmetrical about the diagonal AC. 5. A semicircle ACB has one line of symmetry, namely the perpendicular bisector of a diameter AB. Method. Let ACB is a semicircle and PQ is the perpendicular bisector of diameter AB. If we fold a semicircle along the line PQ, we find that the two parts of it coincide with each other. Hence, the semicircle ACB is symmetrical above the perpendicular bisector of diameter AB. 6. An isosceles triangle trapezium has one line of symmetry, namely the line joining the midpoints of the bases of the trapezium. Method. Let ABCD be the isosceles trapezium in which AB is parallel to DC and AD equals BC. Let E and F be the midpoints of AB and DC respectively. Let E and F be the midpoints of AB and DC respectively. If we fold the trapezium along the line EF, we find that the two parts of it coincide with each other. Hence, the trapezium ABCD is symmetrical about the line EF. 7. The rectangle has two lines of symmetry, each one of which being line joining the midpoints of opposite side. Method. Let ABCD be the given rectangle and let P and Q be the midpoints of AB and DC respectively. Now, if we fold the rectangle along PQ, we find that the two parts of it coincide with each other. Hence, rectangle ABCD is symmetrical about the line PQ. Similarly, if R and CS are the midpoints of AD and BC respectively, then rectangle ABCD is symmetrical about the line RS. 8. A rhombus is symmetrical about each one of its diagonals. Method. Let ABCD be the rhombus. Now, if we fold it along the diagonal AC, we find that the two parts coincide with each other. Hence, the rhombus ABCD is symmetrical about its diagonal AC. Similarly, the rhombus ABCD is symmetrical about its diagonal BD. 9. A square has four lines of symmetry, namely the diagonals and the lines joining the midpoints of its opposite sides. Method. Let ABCD be the given square and EFGH be the midpoints of AB, DC, AD and BC respectively. Then it is easy to see that it is symmetrical about each of the lines AB, AC, BD, EF and GH. 10. The equilateral triangle symmetrical about each of one of the bisectors of these interior angles. Method. Let ABC be the equilateral triangle and let AD, BE and CF are the bisectors of angle A, angle B and angle C respectively. Then it is easy to see that ABC is symmetrical about each of the lines AD, BE and CF. 11. A circle is symmetrical about each of its diameters. Thus, each diameter of a circle is an axis of symmetry. Method. Here, a number of diameters of a circle have been drawn. It is easy to see that the circle is symmetrical about each of the diameters drawn. Hence, a circle has an infinite number of lines of symmetry. Remarks. 1. A scalene triangle has no line of symmetry. 2. A parallelogram has no line of symmetry. 12. Each of the following capital letters of an English alphabet is symmetrical about a dotted line or lines as shown. Rotational symmetry. Look at the given figure. This figure has no line of symmetry. But if we rotate it by 90 degree, 180 degree, 270 degree or 360 degree about its center point O, it looks exactly the same as shown below. Such figures are said to possess rotational symmetry. Thus, a figure is said to have rotational symmetry if it fits onto itself more than once during a complete rotation. The fixed point above the which object is located is called the center of rotation. In the above figure, O is the center of rotation. An angle through which a figure can be rotated to look exactly the same is called an angle of rotational symmetry or simply an angle of symmetry. Thus, for the given figure, the angles of symmetry are 90 degree, 180 degree, 270 degree and 360 degree. So, the above figure has four angles of symmetry. The number of times a figure fits onto itself in a complete rotation is called order of rotational symmetry. It is always equal to the number of angles of symmetry a figure has. Clearly, the given figure has a rotational symmetry of order 4. Note, when any figure is rotated by 360 degree, it comes back to its original position. So, 360 degree is always an angle of symmetry. Hence, if any figure looks exactly the same only after a complete rotation, we say that it does not possess rotational symmetry. Illustrative examples. 1. Let us rotate an equilateral angle ABC through 120 degree, 240 degree and 360 degree to attain the position shown in figure 3, 2, 3 point, figure point 2, figure point 3, figure and figure point 4 respectively. Clearly, each of the 3 times the figure fits onto itself. So, it has a rotational symmetry of order 3. 2. Let us rotate a square ABCD given in figure 1 through 90 degree, 180 degree, 270 degree and 360 degree to attain the position shown in figure point 2, figure point 3, figure point 4 and figure point 5 respectively. Clearly, each of the 4 times the figure fits onto itself. Thus, the given figure, so it has a rotational symmetry of order 4. 3. If we rotate the adjoining figure to 90 degree, 180 degree, 270 degree and 360 degree, then each time that figure will fit onto itself. Thus, the given figure has a rotational symmetry of order 4. 4. Each of the letters H, I, N, O, S, X and Z has a rotational symmetry of order 2. Since each one of these letters when rotated through 180 degree and 360 degree will fit exactly onto itself each time. 5. The adjoining figure will rotate it through 120 degree, 240 degree and 360 degree will fit exactly onto itself each time. So, it has a rotational symmetry of order 3. Notes 1. Rotating a figure through 90 degree clockwise is the same as rotating it anti-clockwise to 270 degree. 2. Rotating a figure to 180 degree clockwise is the same as rotating it anti-clockwise to 180 degree. Figures having line symmetry and rotational symmetry. As a consequence of an examples given below, we can cite the following examples. 1. A square has 4 lines of symmetry, namely the diagonals and the lines joining the midpoints of opposite sides. Also, a square has rotational symmetry of order 4 when rotated through 90 degree, 180 degree, 270 degree and 360 degree. 2. A rectangle has two lines of symmetry, namely the lines joining the midpoints of its opposite sides. Also, a rectangle has rotational symmetry of order 2 when rotated through 180 degree and 360 degree. 3. An equilateral triangle has three lines of symmetry, namely the bisector of its interior angles. Also, an equilateral triangle has rotational symmetry of order 3 when rotated through 120 degree, 240 degree and 360 degree. 4. The letter H has two lines of symmetry. Also, H has a rotational symmetry of order 2 when rotated through 180 degree and 360 degree. Similarly, the letter I has two lines of symmetry when rotational symmetry of order 2. Similarly, each of the letters O and X has two lines of symmetry and rotational symmetry of order 2. 5. An isosceles triangle has a line of symmetry but does not have rotational symmetry. 6. Look at the adjoining figure. It has three lines of symmetry shown by dotted lines. Also, it has rotational symmetry of order 3 when rotated through 120 degree, 240 degree and 360 degree. Rotational symmetry of figures with radial arms. A figure with radial arms possesses rotational symmetry only when the arms are equally inclined to each other. That is, when the angles between every two adjacent radial arms are equal. Thus, a figure with four radial arms, as shown below, will have rotational symmetry only if each angle between adjacent arms measures 360 degree by 4 equals 90 degree. Thus, the above figure possesses rotational symmetry of order 4 and the angles of symmetry are 90 degree, 180 degree, 270 degree and 360 degree. A figure with three radial arms will have rotational symmetry only if each angle between the adjacent arms measures 360 degree by 3 equals to 120 degree. Thus, the above figure possesses rotational symmetry of order 3 and the angles of symmetry are 120 degree, 240 degree and 360 degree. 1. Can you draw a figure such with radial arms that has exactly 5 angles of symmetry? B. Exactly 6 angles of symmetry. Also find the angles of symmetry in each case. Solution. A. Clearly the figure will have 5 radial arms and the measure of each angle between two adjacent arms is equal to 360 degree by 5 equals to 72 degree. The required figure will have rotational symmetry of order 5 and the angles of symmetry will be 72 into 1, 72 into 2, 72 into 3 degree, 72 into 4 degree, 2 into 4 degree and 72 into 5 degree, that is 72 degree, 144 degree, 260 degree, 288 degree and 360 degree. B. Clearly, the figure will have 6 radial arms and the measure of each angle between two adjacent arms equals to 360 degree by 6 equals to 60 degree. 2. Consider a figure with radial arms having exactly 7 angles of symmetry. What will be its smallest angle of symmetry? Is the number of degrees a whole number in this case? If not, express it as a mixed fraction. Solution. As discussed above, it is clear that smallest angle of symmetry equals to angle between two adjacent arms equals to 360 degree by 7 equals to 551 whole 3 by 7. Clearly, the required angle measure is not a whole number of degrees. Rotational symmetry of regular polygons. All regular polygons possess rotational symmetry of order n, where n is the number of sides of a polygon. So, the smallest angle of symmetry for a regular polygon of n sides is 360 degree by n. To understand this clearly, we will consider it as an extension of the concept of rotational symmetry of figures with radial arms. The following figures will make the idea more clear and understandable. Thus, 1. An equilateral triangle has rotational symmetry of order 3 and the angles of symmetry are 120 degree, 240 degree and 360 degree. 2. A square has rotational symmetry of order 4 and angles of symmetry are 90 degree, 180 degree, 270 degree and 360 degree. 3. A regular pentagon has rotational symmetry of order 5 and the angles of symmetry are 72 degree, 144 degree, 260 degree, 288 degree and 360 degree. 4. A regular hexagon has rotational symmetry of order 6 and the angles of symmetry are 60 degree, 120 degree, 180 degree, 240 degree, 300 degree and 360 degree. From the above results, we can conclude that if the angles of symmetry are whole number of degrees, then each of them is a factor of 360 degree. 3. Find the angles of symmetry for the given figures about the point marked. Solution. 1. The given figure will look exactly at the same when rotated by 90 degree, 180 degree, 270 degree or 360 degree. So its angle of symmetry are 90 degree, 180 degree, 270 degree and 360 degree. 2. The given figure will look exactly the same only after one complete rotation. So its angle of symmetry is 360 degree. 3. The given figure will look exactly the same when rotated by 180 degree or 360 degree. So its angles of symmetry are 180 degree and 360 degree. 4. Which of the following figures have more than one angle of symmetry? Solution. 1. The given figure will look exactly the same when rotated by 90 degree, 180 degree, 270 degree or 360 degree. So it has four angles of symmetry: 90 degree, 180 degree, 270 degree and 360 degree. 2. The given figure will look exactly the same when rotated by 120 degree, 240 degree or 360 degree. So it has three angles of symmetry: 120 degree, 240 degree and 360 degree. 3. The given figure will look exactly the same when rotated by 120 degree, 240 degree or 360 degree. So it has three angles of symmetry: 120 degree, 240 degree, 360 degree. 4. The given figure will look exactly the same when rotated by 90 degree, 180 degree, 270 degree or 360 degree. So it has four angles of symmetry: 90 degree, 180 degree, 270 degree or 360 degree. The given figure will look exactly the same when rotated by 90 degree, 180 degree, 270 degree and 390 degree, 180 degree, 270 degree or 360 degree. 6. The given figure will look exactly the same when rotated by 72 degree, 144 degree, 260 degree, 288 degree or 360 degree. So it has 5 angles of symmetry: 72 degree, 144 degree, 260 degree, 288 degree and 360 degree. 7. The given figure will look exactly the same only when rotated by an angle of 360 degree. So it has only one angle of symmetry, 360 degrees. 5. Give the order of rotational symmetry for each figure. Solution. 1. The given figure will look exactly the same when rotated by 180 degree or 360 degree. So it has rotational symmetry of order 2. 2. The given figure will look exactly the same when rotated by 180 degree or 360 degree. So it is also the rotational symmetry of order 2. 3. The given figure will look exactly the same when rotated by 60 degree, 120 degree, 180 degree, 240 degree, 300 degree or 360 degree. So it has a rotational symmetry of order 6. 4. The given figure will look exactly the same when rotated by 120 degree, 240 degree or 360 degree. So it has rotational symmetry of order 3. 5. The given figure will look exactly the same when rotated by 90 degree, 180 degree, 270 degree or 360 degree. So it has rotational symmetry of order 4. 6. The given figure will look exactly the same when rotated by 72 degree, 144 degree, 260 degree, 288 degree or 360 degree. So it has rotational symmetry of order 5. 6. In the given figure, 60 degree is the smallest angle of symmetry. What are the other angles of symmetry of this figure? 2. In the figure, 60 degree is an angle of symmetry. The figure is 2 angles of symmetry less than 60 degree. What is the smallest angle of symmetry? Solution. 1. Clearly, the other angles of symmetry are 60 into 2, 16 to 3, 16 to 4, 16 to 5, 16 to 6. That is 120 degree, 180 degree, 240 degree, 300 degree and 360 degree. 2. Let the smallest angle of symmetry be 2. Then the angles of symmetry are x2 equals to 2 into 3 into 3x is equal to 60 degree. X is equal to 20. Hence, the smallest angle of symmetry equals 20. Rotational symmetry of circles. We already know that every circle has an infinite number of lines of symmetry, namely its diameters. Let us now discuss rotational symmetry of a circle. When we rotate a circle clockwise or anti-clockwise, it consists with itself at all positions, no matter what the angle of rotation be. So, every angle is an angle of symmetry for a circle. Hence, we may say that a circle has an infinite number of angles. Symmetry of a circle has a rotational symmetry of infinite order. But this is not the case with circles divided into sectors as shown below. Thus, if a circle is divided into an identical center, then 1. It has n lines of symmetry. 2. It has rotational symmetry of order n. smallest angle of symmetry A equals 360 degree by n. 4. Its angle of symmetry are A2, A3A equals 360 degree. 7. Do you know that the Ashok Chakra at the center of our national flag has 24 spokes? How many lines of symmetry and angles of symmetry does the Ashok Chakra have? Solution. Clearly, the Ashok Chakra has 24 lines of symmetry as shown alongside. 12 lines passing through 12 opposite pairs of spokes and 12 lines passing between two consecutive spokes. Now, angle between two adjacent spokes equals to 360 by 24 degree equals 50 degree. Therefore, number of angles of symmetry equals to 360 degree by 50 degree equals to 24. 8. Shade the sector of the adjoining circle so that the figure has 1. 3 angles of symmetry, 2. 4 angles of symmetry. What are the possible numbers of angles of symmetry you can obtain by shading the circles in different ways? Solution. 1. The given circle has 12 sectors in all. For 3 angles of symmetry, we need to have 3 identical sets of 4 sectors each, as shown below. The above circle will look exactly the same on turning through 120 degree, 240 degree and 360 degree. 2. For 4 angles of symmetry, we need to have 4 identical set of 3 sectors each as shown below. The above circle will look exactly the same on turning through 90 degree, 180 degree, 270 degree or 360 degree. Now the given circle has 12 sectors in all. The factors of 12 other than 1 are 2, 3, 4, 6 and 12. So the given figure can have 1. 2 angles of symmetry. If we shade and prepare 2 identical sets of 6 sectors each. 2. 3 angles of symmetry as shown. 3. 4 angles of symmetry as shown. 4. 6 angles of symmetry if we shade and prepare 6 identical sets of 12 sectors each. 5. 12 angles of symmetry if we leave it unshaded. Hence, the possible values of number of angles of symmetry are 2, 3, 4, 6 and 12.